Good day everyone. Today, we will discuss about the interface and intraphase mass transfer.
So before anything else, we must review what is mass transfer first. As some of us may already know, mass transfer is mass in transit as a result of a difference in concentrations of a species in a mixture. When two phases of different compositions are brought into contact, component transfer may occur from one phase to another or vice versa. This is the physical basis of mass transfer operations. If the two phases are in contact for a sufficient period of time, they eventually reach equilibrium, and thereafter, there is no longer a net transfer of components between them. In most cases of interest to mass transfer operations, the two phases are only partially miscible, so that in equilibrium there are still two phases that can be separated from each other. Usually, these two phases have different compositions, and these compositions are also different from those of the phase at that time of initial contact. Therefore, the relative quantities of the components that are transferred between the phases are different, so that a separation between them is achieved.
Unit operations that involve mass transfer are distillation, gas absorption, desorption, liquid-liquid extraction, solid-liquid extraction, and adsorption.
There are three mechanisms of mass transfer: interface diffusion, migration, and convection. For interface diffusion, the random movement of molecules is from a region of high concentration to regions of lower concentration. The rate at which a molecule diffuses is dependent upon the difference in concentration between 2 points in solution, called the concentration gradient, and on the diffusion coefficient D, which is a characteristic value for a specific solution species at fixed temperature. The movement of a chemical species under the influence of a concentration gradient is described by Fick's first law. A particle I will diffuse through a cross-sectional area as a function of concentration gradient across the selected area. Flux, as particles per unit time across the given segment, is expressed as J sub I according to the given formula, where the partial derivative dci over dx expresses the concentration gradient. D sub I is the diffusion coefficient for particle I.
Movement of charged particles in response to a local electric field is called migration. The contribution of this to the total flux is proportional to the charge of the ion, its concentration, diffusion coefficient, and the magnitude of the electric field gradient experienced by the ion. A change in the applied potential to a solid electrode in a solution containing ions affects charge migration for increasing negative charge at the electrode surface.
Convection. The movement of fluids is described by hydrodynamics. Applies to electrochemistry is forced movement of solution species by mechanical or other means.
And now, let's talk about interface mass transfer. The transport of mass within a single phase depends directly on the concentration gradient of the transporting species in that phase. Mass may also transport from one phase to another, and this process is called interface mass transfer. Many physical situations occur in nature where two phases are in contact, and the phases are separated by an interface. Like single-phase transport, the concentration gradient of the transporting species, in this case in both phases, involves the overall rate of mass transport. More precisely, transport between two phases requires a departure from equilibrium, and the equilibrium of the transporting species at the interface is of principal concern. When a multi-phase system is at equilibrium, no mass transfer will occur. When a system is not at equilibrium, mass transfer will occur in such a manner as to move the system towards equilibrium.
For the key points, many industrial reactions are carried out at high temperatures where the overall rate of reaction is limited by the rate of mass transfer of reactants. By mass transfer, we mean diffusion plays a role and we cannot directly use the rate laws. Now we have to consider under the fluid velocity properties when writing the mole balance. We will discuss how to determine the rate of reactions and how to size reactors when their reactions are limited by mass transfers.
Diffusion fundamentals. Diffusion is a spontaneous intermingling or mixing of atoms or molecules by random thermal motion. it gives rise to motion of the species relative to the motion of mixture. In the absence of other gradients such as temperature, electric potential, or gravitational potential, molecules of a given species within a single phase will always diffuse from regions of higher concentrations to regions of lower concentrations. This gradient results in a molar flux of the gradient. We now apply the mole balance to species A, which flows and reacts in an element of volume. Change in V is equal to the product of change in X, change in Y, and change in Z, to obtain the variation of a molar fluxes in 3 dimensions. This figure shows the fundamentals of diffusion.
Diffusion through a stagnant film. Reaction takes place only on the external catalyst surface and not in the fluid surrounding it.
So we have here figure 14-3, which illustrates the concentration profile for dilute concentration in stagnant film mode. So from the concentration CaO to CaS, with a reference of Z equal to 0 and Z is equal to the small delta. So we have the very fundamental equation here, which is the flux WAZ is equal to negative DAB times dCA over dZ. So simplifying this equation and integrating it, we obtain the formula Ca is equal to CAS plus the quantity of CAB minus CAS times Z over small delta. And further simplifying it, and if we want to solve for the flux WAZ, we can use the formula WAZ is equal to DAB over small delta times the quantity of CAB minus CAS.
While the boundary layer thickness will vary around the sphere, we will take K sub C equals to diffusivity divided by gamma. Combining this equation with the 26, we obtain the average molar flux from the back fluid to the surface. In the stagnant film model, we consider all the resistance to mass transfer to be lumped in the thickness, gamma, and then the reciprocal of the mass transfer coefficient can be thought of as the resistance.
The mass transfer coefficient is analogous to the heat transfer coefficient. The heat flux from the bulk fluid at an initial temperature to a solid surface at Ts is given by the formula Qz. For forced convection, the heat transfer coefficient is normally correlated in terms of 3 dimensionless groups, and they are the Nusselt number, the Reynolds number, and the Prandtl number. For the single spherical pellets discussed here, the Nusselt number and the Reynolds number take the following forms.
The Prandtl number is not dependent on the geometry of the system. It is equated with the equation given, where the symbols are defined as follow.
Transfer correlation relating the Nusselt number to the Prandtl and Reynolds number for flow around the sphere is this formula. When the Reynolds number becomes 0, the Nusselt number becomes 2. And at higher Reynolds number in which the boundary layer remains laminar, we can neglect the 2. Thus, the Nusselt number will become 0.6 times the square root of Reynolds and then times the cube root of your Prandtl number.
In this slide, we are being shown how the Sherwood number is derived. So the Sherwood number is the ratio of the convective and the conductive heat transfer at the boundary in a fluid. It is also called the Nusselt number used in mass transfer. It has the formula Kc times dP over dAB, and it is a dimensionless number like the Reynolds number. So it has been derived from Qz is equal to H times T minus Ts, which is the heat flux Qz, and the mass transfer flux, which is WAZ, is equal to Kc times the quantity of Ca minus Cas.
Schmidt number is dimensionless and is equal to V over dAB, where Flushing correlation is equal to 2 plus 0.6, Reynolds number raised to 0.5, and Schmidt number raised to 1/3.
The following are the formulas when speaking of mass transfer correlations. For turbulent flow, mass transfer to a pipe wall has its own formula. Well, the same goes with mass transfer to a single sphere, mass transfer in fluidized beds, and mass transfer to packed beds. They all have their own respective formulas.
Here is a sample problem. A rapid reaction on the surface of a catalyst. Calculate the molar flux of reactant A to a single catalyst pellet 1 cm in diameter, suspended in a large body of liquid B. The reactant is present in dilute concentrations, and the reaction is considered to take place instantaneously at the external pellet surface. The bulk concentration of reactant A is 1 molar, and the free stream liquid velocity past the sphere is 0.1 meter per second. The kinematic viscosity is 0.5 centistoke, and the liquid diffusivity of A and B is equal to 10 raised to negative 10 meters squared per second at 300 Kelvin.
So let us now proceed to the solution for the problem. So we have the formula for the radial flux, which is WAR is equal to Kc times CAB minus CAS. And because this reaction is assumed to occur instantaneously on the external surface of the pellet, CAS will be assumed to be equal to 0. And also CAB is given as 1 mole per dm cube, and we will use the Frosting correlation, which is equal to the Sherwood number equal to 2 plus 0.6, Reynolds number raised to 1/2, and the Schmidt number raised to 1/3. So let us first solve the Reynolds number, which is equal to dpu over v. So our dp, or the diameter of the pellet, is 0.01 meter, and our u, which is the free stream liquid velocity, is 0.1 meters per second over the kinematic viscosity, which is equal to 0.5 times 10 to the power of negative 6 meters squared per second. So solving the Reynolds number, we obtain 2000, and for the Schmidt number, it is equal to v over dAb. So our v is equal to 5 times 10 to the power of negative 7 meters squared per second, and our dAb, which is equal to 10 to the negative 10 meters squared over second, which is equal to 5000. So we will be using now the values of the Re, of the Reynolds number, and the Schmidt number we solved earlier. So we will substitute it in the Frosting equation, and we will obtain the Sherwood number to be 460.7. And we will use the Sherwood number to solve for Kc, with the equation Kc is equal to dAb over dP times the Sherwood number. And substituting the known values, we obtain Kc to be 4.61 times 10 to the power of negative 6 meters per second. And we were given with the value of the CAB on the problem to be 10 to the cube mole per meter cube. And substituting Kc and CAB into equation 14-26, we obtain the molar flux of the surface to be 4.61 times 10 to the power of negative 3 mole per meter squared times second. And we know that the radial flux is equal to negative RAS raised to n, and hence we have the negative RAS raised to n to be equal to 0.0046 mole per meter squared times second, or 0.46 mole per dm cube times second.
Mass transfer dominated reactions, the surface reaction is so rapid that the rate of transfer of reactant to the surface limits the overall rate of reaction. Mass transfer limited reactions respond differently to changes in temperature and flow conditions. We begin by carrying out a mole balance of the generic mass transfer limited reaction carried out in a packed bed reactor, that is molar rate in minus molar rate out plus molar rate of generation is equal to molar rate of accumulation.
From the previous equation, R double prime A is the rate of generation of A per unit of catalytic surface area. AC is the external surface area of catalyst per volume of catalytic bed, or the volume of solid over the volume of the bed multiplied by the surface area over the volume of solid. The omega is the porosity of the bed, dP is the particle diameter in meter, and AC is the cross-sectional area of tube containing the catalyst.
We could actually derive some useful formulas using equation 14-51. By dividing equation 14-51 by AC change in z, and taking its limit as change in z approaches 0, we will obtain equation 14-52. And now we now need to express FAZ, or the molar flow rate of A, and R sub A raised to n in terms of concentration. We know that the molar flow rate of A, or FAZ, is equal to AC WAZ, but we also know that WAZ is just equal to JAZ plus VAZ, where JAZ is the amount of material transported by diffusion or dispersion in the axial direction, while VAZ is the amount of material transported by convection. And hence we have the equation 14-53. But we also know that JAZ is actually negligible when compared to BAZ, and hence we can neglect JAZ and remove it from the equation, and hence we have the equation 14-54. And now we will be substituting the new expression for FAZ into the equation 14-52, and we will obtain the equation 14-55.
Constant superficial velocity u, you will have the formula negative u times dCA divided by dZ plus the rate of generation of A per unit of catalytic surface area times the external surface area of catalyst per volume of catalytic bed equals to 0. Focusing on the figure below, for reactions at steady state, the molar flux of A to the particle surface, which is W of AR, is equal to the rate of disappearance of A on the surface.
We have here some additional formulas that we might be able to use. So from the radial flux, we have the rate of reaction, negative R sub A raised to N is equal to the radial flux WAR is equal to Kc over Ca minus Cas. So the equation 14-59 was derived from the equation 14-56 on the previous slide. We just substitute negative Ra raised to N with Kc times Ca minus Cas from 14-58. And other important formulas to use will be Ca over Cao is equal to E raised to the quantity of negative KCAC over U times Z. And we have here the corresponding variation of the reaction rate along the length of the reactor, which is the negative R is equal to KCCAO times E raised to the quantity of negative KCAC over U times Z.
Concentration and conversion profiles down a reactor of length R are shown in this figure. To determine the reactor length L necessary to achieve a conversion X, we combine the definition of conversion, that is X equals to CAO minus CAL over CAO. The evaluation of equation 14-61 at Z equals to L to obtain ln of 1 over X is equals to KC AC over U times L.
When the porosity is between 0.25 and 0.5, and Re prime between 40 and 4000, and Schmidt number between 1 and 4000, we will use equation 14-65 and 14-66, where Re prime is equal to the Reynolds number over 1 minus omega multiplied by gamma. Sh prime is equal to Sh times omega over 1 minus omega multiplied by gamma. dP is the particle diameter, the omega is the void fraction of packed bed, the gamma is the shape factor, and the U, ρ, mu, V, and dAV are as previously defined.
Sample problem: mass transfer effects in maneuvering a space satellite. Hydrazine has been studied extensively for use in monopropellant thrusters for space flights of long duration. Thrusters are used for altitude control of communication satellites. Here, the decomposition of hydrazine over a packed bed of alumina-supported iridium catalyst is of interest. In a proposed study, a 2% hydrazine and 98% helium mixture is to be passed over a packed bed of cylindrical particles 0.25 cm in diameter and 0.5 cm in length, at a gas phase velocity of 150 meter per second and a temperature of 450 Kelvin. The kinematic viscosity of helium at this temperature is 4.94 times 10 to the negative 5 meters squared per second. The hydrazine decomposition reaction is believed to be externally mass transfer limited under these conditions. If the packed bed is 0.05 meter in length, what conversion can be expected? Assume isothermal operation. For additional information, d sub AV is equal to 0.69 times 10 to the negative 4 meters squared per second at 298 Kelvin. For the bed porosity, 40%. Bed fluidicity, 95.7%.
So let's discuss the solution for this problem. So as you can see in your screen, you have there the equation for the conversion that we will be using later when we already solve Kc. So the first part of the solution, we will be using the Thonis and Thonis-Kramer's correlation in order for us to calculate the Kc. So we need to find first three important variables for us to proceed to the solution. The first one is the volume average particle diameter. The second one is the surface area per volume of bed, and the third one is the mass transfer coefficient. So to find the volume average particle diameter, we'll be using the formula, the quantity of 6V over pi raised to 1/3. And since the volume of a cylinder is equal to pi d squared over 4 times L, we will have the, and simplifying that, we will obtain 1.5 d squared times L, quantity raised to 1/3. And substituting known values, we obtain 3.61 times 10 to the power of -3 meters. And in the calculation of the area per volume of bed, we have AC is equal to 6 times the quantity of 1 minus 0.4 times the dP we solved in the previous part. And substituting known values, we obtain 998 meter squared over meter cubed. And lastly, for the mass transfer coefficient, we will solve for the Reynolds number, which is equal to the dP U over V. And substituting known values, we obtain 10,942.
For cylindrical pellets, the shape factor is equal to 2 pi times R times LP plus 2 pi times R squared, all to be divided by pi times the particle diameter squared. The prime of Reynolds number is just the Reynolds number divided by the quantity 1 minus void factor times the shape factor. And by correcting the diffusivity to 450K using the table 14-2 gives us 1.42 times 10 to the -4 meters squared per second.
For our Schmidt number, our V is equal to 4.94 times 10 to the -5, and DAB is equal to 1.42 times 10 to the -4, which will be equal to 0.35. The SH prime will be equal to 86.66, and our KC will be equal to 6.15 meters per second. For our conversion, we will have 0.87, which is equal to 87%.
Use Colborn-JD factor to calculate K sub C. To find K sub C, we first calculate the surface area average particle diameter. For cylindrical pellets, the external surface area is this formula, and we found that the diameter would be 3.95 times 10 to the -3 meters, and then the A sub C to be equal to 910.74 meters squared per meter cubed. So for the Reynolds number to be dPu over V, which is equal to 11,996. And then we solve for JD using this formula, and then we found that JD equals to 0.25. And SH, using this formula again, we found that SH will be equal to 212. We solve for K sub C to be equal to DAV over dP times SH to be equal to 7.63 meter per second. And then your conversion will be now equal to 0.9. If there is such a thing as the fluidicity, given in the problem statement, it would be a useless piece of information. Make sure that you know what information you need to solve problems and go after it.
We have here a sample problem, the case of divide and be conquered. A mass transfer limited reaction is being carried out in two reactors of equal volume and packing, connected in series as shown in figure E14-3.1. Currently, 86.5% conversion is being achieved with this arrangement. It is suggested that the reactors be separated and the flow rate be divided equally among each of the two reactors to decrease the pressure drop and hence the pumping requirements in terms of achieving a higher conversion. Robert is wondering if this is a good idea.
To discuss the solution for this problem, so we will use the equation 14-64, which is the ln of the quantity of 1 over 1 minus x is equal to Kc times AC over U times L. So we'll use that for case 1. So the case 1 is the undivided system as shown in the figure E.14-3.1. So we will have the equation ln of the quantity of 1 over 1 minus x1 is equal to Kc1 AC over U1 times L1. And we already know that x1 is equal to 0.865.
For case 2, the divided system would be this formula. And we now take the ratio of case 2 to case 1 and we obtain the formula Kc2L2 U1 over Kc1L1 U2. The surface area per unit volume AC is the same for both systems. From the condition, we know that L2 equals to 1 half L1, U2 equals to 1 half U1, and X1 to be 0.865, and we don't know yet X2. However, we must consider the effect of the division on the mass transfer coefficient, and from equation 14-70 we know that Kc is directly proportional to the square root of U. Then, Kc2 over Kc1 is now equal to the square root of U2 over U1. Multiplying by the ratio of superficial velocity yields this formula, and solving for x2 gives us 0.76. Consequently, we see that although the divided arrangement will have the advantage of a smaller pressure drop across the bed, it is a bad idea in terms of conversion. But we need to recall that if the reaction were reaction rate limited, both arrangement would give the same conversion.